We learn early that our innovations are only as strong as the foundations they are built on. Build them with strong support, and they will soar. Engineering innovations are no different. Without a strong foundation, successfully developing and deploying them will only get harder. Because as design complexity continues to rise, and time to market cycles shrink, siloed design and test workflows will be pushed to their limit. Today's enterprises are striving for digital transformation, striving to develop and deploy technologies at market speed, striving to improve execution within and across development teams, striving to make agile, well-informed strategic business decisions. As a company with deep roots in engineering, at Keysight, we understand. It's why we've created the PathWave platform, a complete data sharing and solution building platform that enables agile, integrated design and test workflows, no matter how large or small your enterprise. The PathWave platform is the strong foundation you need to master your next innovation. It streamlines your development process, speeds your time to deployment, and gives you insights to make better, faster decisions. Are you ready to accelerate digital transformation in your engineering enterprise? Contact Keysight to learn more about the PathWave platform today. Discover the strongest foundation to help your business soar.
Hello, and welcome to today's webinar. My name is HeeSoo Lee, and I'm the product owner for SerDes and DDR product here at Keysight Technologies. I have an informative MIPI C-PHY presentation prepared for you today, which will be followed by a question and answer session. So please feel free to submit any question at any time during the presentation. I will answer those questions as much as possible. All right, then let's get started. The agenda for today's presentation is to start with MIPI physical layer overview. Then we'll talk about simulation challenges and solution specific to MIPI C-PHY. And then we'll talk about OpenEye solution space exploration study. Then I'll do the demo on the solution and go for the summary. So MIPI, what is it? The full name of MIPI is Mobile Industry Processor Interface, based on the serial interface standard. Many of the interfaces are moving to serial interfaces is because of several reasons. For example, parent interfaces are very difficult to expand and also require a lot of interconnects and so on and so on. When you look at the other one of the picture in this slide that shows the 5G MIPI interfaces, in mobile applications, there are a lot of devices are used that comes with its own standard. If we keep all the interface standard as proprietary interfaces, it will be very difficult for design engineers to develop a new devices or a new system, because every single time it needed to be redone. That's why the new standard for those interfaces for mobile application was developed, which was basically MIPI. MIPI is used for a lot of different applications, not only smartphones, including the tablets and drones and IoT, even expanding the solution to automotive applications. MIPI organization actually provides a set of specialized physical layers to support various applications, including MPI, DPI, and C-PHY, as well as API. MPI is the physical layer performance-driven, used for UFS memory interface as well as inter-process communications. DPI and C-PHY are high-performance, cost-optimized physical layer extensively used for camera and display applications under CSI and DSI. CSI stands for Camera Serial Interface. DSI stands for Display Serial Interface. A-PHY, which is still under a development, is the physical layer used for autonomous driving and other automotive applications. For D-PHY, the current version is version 2.1, which was the one released March 2017. There are two modes. One is high-speed modes, and the other is low-power modes. As you see in this table, conditions are a little bit different. For example, under high-speed modes, the signaling is differential. For low-power modes, the signaling is single-ended. Speed-wise, it can go up to 4.5 gigabit per second with equalizations. When we look at a typical configuration, which comes with one side with the transmitters, the other side receiver in between, there are channels. There is one clock lane, and there are max up to 4 data lanes. In case of C-PHY, similar to D-PHY, there are two modes, high speeds and low power. The current specification is version 2.0, which was the one released September 2019, and supports up to 8 giga sample per second with a RX equalization for short channel and 6 gig for a standards and 4 gig for long channel. There are channel compensation techniques are used, one with the advanced TX equalization and the other with a RX Ctle. The one makes C-PHY quite unique is the one that it uses three-phase system, meaning that it uses the three wires to transfer the data to the receiver. So as you could see in this picture, one lane is basically trio, having three wires to send all the data transmission through the channel. Okay, this is a summary slide that talks about different MIPI physical layers containing MPI, D-PHY, and C-PHY. Since this is a busy slide, I'm not going through every single line, but please keep that in mind. MPI is the one performance-driven, especially for multimedia and chip-to-chip inter-process communication applications, and D-PHY and C-PHY are extensively used physical layers for cameras and displays. In terms of a lane or channel, MPI supports up to 10 ports, which means 4 lane of TX and 1 lane of RX. And for D-PHY, similarly, it supports up to 4 lanes for data and 1 lane for clock. However, C-PHY, since it is using the three-phase signaling, it takes the 9 up to 3 lanes. So that is one thing which is different of C-PHY compared to the other physical layers like MPI and D-PHY. Okay, let's discuss MIPI C-PHY simulation challenges and solutions in detail level. As a C-PHY design engineer, what is your typical C-PHY simulation challenges you have as of today? These are the list of challenges I found during the development of a C-PHY solution. Let me start with the first one. There wasn't a very easy to use transmitter and receiver available, which means modeling itself of the transmitter and receiver is quite complicated a process, especially with the equalizations. So we really need some transmitter and receiver models we can just easily drop down and start to design the C-PHY. Due to that complexity, there are a lot of different tools involved, including a very low gain. That actually means a lot of customization to make it work. So we really need just a simple one, a single platform solution that doesn't require much of customizations of the tools. Technically, we got to do a lot of jitter analysis to make sure the system is clean, especially for RJ, PJ, and DCD, duty cycle distortion jitter. The tools are limited that allows C-PHY engineers to do all of those jitter analysis. In the past, the baseline simulator was more like a SPICE. That makes sense when the device is under development, just running for a few hundred bits. But shooting for a lower BER, that requires millions of bits a simulation. And also, speaking of the RJ, randomness of the jitter, we really need to run more number of bits to make sure the system works. This is almost impossible with a SPICE-like simulators. The other was, based on the C-PHY specification, the I data must be triggered. Instead of just placing or plotting the data based on 2 UI, unit interval, I needed to be aligned at the clock tick, which is basically a triggered I plots. But it wasn't the case in the past. So again, these are some important list of the other challenges, but as a C-PHY design engineers might have more or something different than this. But let's talk about how these challenges were resolved in a new simulation solution. Okay, let's jump into the solution. This slide really shows a new C-PHY generic modeling solution, what we have in ADS environment as of today. The picture shown to the left is old way. All the green color is all different modeling block. As we talked about from the previous slide, this makes C-PHY design process very, very complicated. Whereas to the right, you basically have dedicated C-PHY transmitter and receiver along with iProbe that comes with triggered eye capability. And this new design environment that really support both transient and channel sim, so that when you are running a complete time domain based simulation with a lower number of bits, you can set the engine to transients. But if you like to go with the millions of bits, where a new engine like a channel sim is required, you can switch it to channel sim and run the simulation without creating the new schematic. And this transmitter supports jitter, such as RJ and PJ, along with the clock DCD. So you can see jitter performance of your system by setting up those numbers very easy. And top of it, equalization, including advanced TX-EQ and Ctle are embedded into this new solution. Going into a little bit more on the detail on TX side, the lower left side picture shows old way of modeling, which is quite complicated. It is now represented with a simple C-PHY TX, which is shown in the middle with the 3 wires. When you open it up, you're going to see the very well tab organized C-PHY source setting. You can set up your own PRBS, pseudo random bit sequence source, and also you can shape it your waveform by putting the number for V high, V mid, V low, rise or fall time, including the edge shaping for the waveforms. Then top of it, definitely you can set up the equalization for TX-EQ, and you'll be able to actually set up the jitter for RJ-PJ and clock DCD, and also being able to set up the electrical characteristic with your transmitter, such as R output nodes, and setting up the levels. So now we know how to construct the transmitter and probably receivers. Let's put the design into a test case. In this example, I was using the TX with a 3.5 giga sample per second data rate and set up the waveform to be 425 millivolts for V high. V mid is set to 212.5 and V low is set to 0, which is the kind of spec data coming from the specification. For rise and fall time, 25 picosecond, set to be a symmetric waveform data. Putting this all in and running the simulation and picking up the I data right after the channel, one with triggered and the other is non-triggered, you can see how the I data is plotted. So looking into the triggered, it looks a bit cleaner than non-triggered. And putting the eye mask into the middle of the eye, we can still see that still there is enough margin for the system. So setting up the TX and RX are very straightforward, as we talked about. The only thing what you need to do is putting your channel. In this case, in this example, I just put the standard channel, which was downloaded from MIPI organization. Putting the TX equalization to the same design. It can be done very easy. I just open up the transmitter and go to the TX equalization tab and put the equalization numbers for EQ M1 plus, minus, and H1, H0, and so on and so on. The numbers what you are seeing is the kind of standard numbers given by the specification. And putting these numbers into it, you can see triggered and non-triggered performing a lot better by having this equalization. So again, we can see the eye opens up and we meet the specification using the standard channel running with the 3.5 giga sample per second. The data rates, it works just fine. Using the same example, what if we push the data rate to higher using the standard channel under same condition, not 3.5 giga sample per second, but running at a 4.5 giga sample per second. Again, same settings for the waveform and with equalizations. As you could see in this slide, non-triggered and triggered data both shows enough margin with the eye mask. So we can test the channel data at running at higher speed grade. That is still working fine. In other words, yes, it still provides a good solution space running at the higher A speed. Now let's talk about jitter. Starting with the RJ, random jitter, was the impact on eye data. The plot on the top is eye data without having of RJ, random jitter. By adding the 1 picosecond small RJ, then we see that 6 millivolts and 7.1 picosecond eye closure with 10,000 bits. But the question is, due to the randomness of RJ, what if we increase the number of bits? Eye closure getting smaller or larger? what will be the change we can see by running through the more number of bits. Let's do that with a 1 million bits. Then we see 19 millivolts and 54.3 picosecond smaller I compared to no RJ. What about increasing number of bits to 10 million bits? Although it takes a lot longer to simulate, but still in minutes range. We see that I closure is about 20 millivolts and 55.7 picosecond smaller I. Comparing 1 million bits and 10 million bits, there is not much of gaining. It's a small a change. However, in terms of simulation time, that was 2 minutes to 13 minutes, which is about a 6x a longer sim time. So it is quite important to run with a more number of bits to ensure the analysis accuracy. But with this test case, we can say we really need to go up to the 1 million bits to ensure good and reasonable or even accurate results coming out for a RJ analysis. How does that even possible to run millions of bits in minutes? This is all possible because of channel simulator that is designed for rapid high-speed signal integrity analysis. Unlike traditional SPICE-like simulators that solve the network problems at every single time step, the channel simulator uses superposition of step or pulse responses of the channel with TX and RX's analog parts in bit-by-bit modes. In case of statistical modes, system properties are derived from statistical calculations, not from the superposition of bit patterns. ADS only supports bit-by-bit modes for C-PHY at this moment. What about other jitters, such as PJ and clock DCD? Putting those numbers into jitter tab and running through the simulations, we get quite interesting data. For PJ, adding the 10 picosecond and 100 megahertz PJ, that results in 30 millivolts and 4.3 picosecond I closure. This tells us that for PJ, it is affecting a more of I height than I width. However, looking into the clock DCD, putting 0.1 DCD, that results in 0 millivolts and 28.5 picosecond I closure. Well, by looking at this data, we can tell clock DCD affects more on the I width than I height. All of this analysis is very simple. By putting together those numbers and rerun, you get the data very quick and gives us the good insights on all different type of jitters. Starting with the C-PHY specification version 2.0, Ctle, continuous time linear equalizer, can be used with the RX. C-PHY Ctle transfer function is shown in this slide that has a 2 poles and 1 0 with a DC gain. We can implement this transfer function in a very simple way in ADS using a VCVS PZR that is a component. Basically, you can define poles and zeros and make it as your own Ctle. By running the simulation with that simple implementation, we can see how Ctle works in the plot to the right in this slide. Now this component is part of ADS C-PHY receiver so that a user can easily set a Ctle values and make it a system works for the OpenEye. This slide shows how Ctle is implemented into C-PHY RX. You can enable Ctle, and then it will pop up Ctle Visualizer, where you can select the C-PHY informative Ctle settings, and then the frequency response of the specific Ctle setting will be shown in the bottom of the window right away. That also shows the poles and zeros on the transfer function in this plot. Let's put this Ctle into a validation test with a 6 giga sample per second with a standard channel case. Poles and zeros for this Ctle was set to 1 gig for 0 and 3 and 9.95 for a pole 1 and pole 2. In this case, ADC was set to 1, having the CPET TX and RX 1 pub and 0.1 pub respectively. Without having Ctle, as you see on the top side of the window, I was completely closed. So we cannot recover. But putting the Ctle with those settings, now you can see that from the middle I data, I opens up quite well, having triggered 120.8 picosecond I width with a non-triggered 117.5 picosecond. But again, by putting the Ctle, we can see that the eye can be open. So far, we discussed about MIPI C-PHY simulation challenges and how those problems are addressed in ADS. Now let's discuss OpenEye solution space exploration study for MIPI C-PHY as for the next topic. So what is exactly OpenEye study? From my perspective, it is pretty clear that most of the C-PHY design engineers will design the channel under a transmitter and receiver condition with a certain pad capacitance attached to it. How you set a proper Ctle, and what kind of a data rate you can actually pass through. These are the things needed to be explored as C-PHY design engineer and make sure the eye can be open under certain condition with a certain settings. In C-PHY specification, we know that there is a target eye mask with a clock jitter. The eye width can be a 0.5 UI, and eye height could be a minus 40 millivolts. Without having the clock jitter, it can go up to 0.65 UI for eye width, and eye height still remains the same, plus minus 40 millivolts. Looking into the schematic shown in this slide, we put TX and we put RX with the pad capacitance for TX and pad capacitance for RX, and in between there is a channel. The CPET TX can be the value in between 1 to 2.5 pub capacitance, and for CPET TX it could be a 0.1 or 1 pub a capacitance. Putting this number, going through all the possibilities of combination of values, that's basically what we're going to do as an OpenEye study for the design. For the test, we are using 3 channels. These 3 channels are basically as parameter data. Starting with the short channel, it's driven by 8 giga sample per second data rate. And for standard channel, 6 gig, long channel is driven by 4 giga sample per second signals. Having 3 channels, short, long, and standard, And we have a different values for CPAD TX, which is varying between 0.5 to 1.5 pub capacitance. And also, same story for RX, having two cases. There are just many different simulations we need to run. By putting a 0.5 pub step size for CPAD TX and having all different pole 1 frequencies, there are around 96 simulations we need to run. That's just too much to do the job one by one. So basically, I'm using a special simulation technology called batch sim, where you can point to Excel CSV file where all the combinations are written. Then I can make it a one single batch job to run through all 96 cases. How did I set that up? As you could see in the picture below, I'm setting up a batch simulation pointing to CSV file that I created for all different combinations. But in terms of simulator, it is pointing to the other channel sim. The setup is pretty straightforward and not too difficult to set up. Okay, this is the results for short channel, which is running at a giga sample per second. So starting with the target specification without having clocked ACD, if you remember, the spec was 0.65 for eye width, and for eye height, that was more like plus minus 40 millivolts. The blue trace on this plot is basically eye opening, calculating eye width. That shows all 96 cases. The data looks quite interesting. It is actually going down eventually, but also it goes up. So how do we interpret this data? But important data I like to tell you about, putting the spec line at 0.65 eye width, we see that out of the other 96 cases, majority of cases we can actually pass the specification. Yes, certainly there are a few cases going under the specification, which is failing to meet the spec. But we can see that exploring entire design space, we can see that, or we can safely say 90% cases may pass the design specification. How can we interpret this plot? As you see in this slide, the up a line, meaning that when you are pushing the pole frequency for FP1, then the value of eye opening goes up. When you are picking up the certain points, which is represented with a green, that's a basically value of a CPAD RX at 0.5 pub capacitance. If we pick up certain points and drew a line, which is orange color, that is the value with a CPAD RX at 1 pub. By looking at this data, in decreasing CPAD RX value will make the eye opening larger. By putting the larger value for CPAD RX, we can say eye will be getting smaller and smaller. The decreasing slope for this green and yellow, the orange, are basically representing increasing value of TX, CPAD TX. So again, by looking at it, it is always important to maintain the smaller value for CPAT, TX, and RX to make up the bigger open eye. This is quite interesting to understand. Again, maintaining the smaller value for a CPAT, TX, and RX will be important, and also using the higher pole 1 frequencies will make up the open eye for most of the cases. But again, we still have a good solution space running through the short channel and going through the all different 96 cases. We have many cases that pass the specification. What about the case with adding a 0.1 clock DCD? As we remember, the target eye mask becomes 0.5, so that the red trace in this plot represent the specification. By adding a clock DCD, we can see that all 96 cases are passing the specification. So we are quite okay, and this design itself is having a really good solution space, because most of 96 cases, whatever the value of CPAT, TX, and RX are used, are passing the specification. Let's take a look on standard channel case. Pretty similar story, but now we're having the different channel. As you can imagine, running the longer a channel than short channel, we are seeing the more cases falling under the spec line, which is eye opening of a 0.65 UI. But we can still say we have a still pretty good solution space, because many of combinations are still above the specification. If you are interested in looking at eye width versus a CPAT TX, you can easily plot the results as shown in this slide. So one case with CPAT RX set to 0.5 pub capacitance, and the other is 1 pub, and you can see that larger value of the CPAT TX will give us the smaller eye, but with the case of 0.5 pub, still all the cases are above the specification. But having the larger value for CPAT TX, there is one case definitely falling under the specification. This can be easily analyzed and plotted like in this slide. With the clock DCD jitter added, then we have a better A margin, as you could see, because the value of the spec is 0.5, and all the cases are all above the spec line, so we can ensure the design will work just fine by looking at the data. This slide shows the case for a standard channel in terms of understanding and how we interpret the data, the same as before for the case of short channel. Another thing what we need to look into is impedance discontinuity of the channel. So we made up the kind of 6 different cases, having a close to the length of the line close to the 12 or 13 inches, and one case definitely going with the strip line to microstrip and having the different length. The important thing is, along with the impedance discontinuity, the question is whether the eye can be open or not with a proper Ctle equalization. So let's put this into the test and see the results. The result shown here is quite promising. Under all different impedance discontinuity conditions, we can see that eye can be still open with proper A equalizations, giving us a still good margin for the design. Okay, now I'm going to do a short demo for you. Alright, this is a project file that I want to demonstrate, and also this was the one I used to develop my presentation. By the way, if you're interested in getting this project, then please go to the MIPI webpage where you can download this entire project file. Otherwise, you can contact us so that we can share this ADS project. I organized the project based on the other different testing and different setup by folder. So let me open up the second one, which is called a MIPI C-PHY feasibility study. To start with, one design, this. When I double click it, I can easily open the design, which is very simple design, having the transmitter and having the channel and also receiver and eye probe to measure at any locations of the channel. And also you can add any other extra design components such as CPAD, TX, and RX like shown in this window. How to set up the C-PHY TX? Just go and then double click it and it will pop up this window where you can set up the PRBS and waveform shaping and equalization and jitter, and adding any of the electrical impedance to the design. Everything is very straightforward throughout this tab settings, tab windows. Once you set that up, then you can do the same thing for receiver, and by double clicking it, you'll be able to see the receiver with Ctle enabled. When I go and then click edit, then it pops up this window where you can choose any of a Ctle settings by using this preset. So if you click and then scroll down, then you'll be able to see C-PHY specific settings of Ctle. So again, if I'm using the C-PHY a standard channel at a pole frequency at 2.4, you can pick that up and immediately show the transfer function. If you want to apply it, go and then click OK. Then your receiver will have the Ctle embedded into the design. So you can go and click apply. And for a eye probe, this was a specially designed eye probe with 3 wires where you can open it up and set up your measurements. You can do all different measurements, including collecting clock signal and waveform data, or just go and calculate the eye density, or calculate the jitter and UI. Everything is just one mouse click. Once you set them up, you can basically choose what engines you're gonna want to use. In this case, I'm going to use the channel sim because I want to run the millions of bits, more bits than transients. So I can enable them and disable the transient. Then I can just go and then click a simulation button. Then we'll be running the simulation. It may take probably less than 20 seconds, or it's already done. Then I can see how the data look like, and if I want to go back and choose the different channel data, the equalization data, you can basically go back and choose the different equalization. For example, when I choose another one and go back to the simulation and rerun, then I'll be able to see the results right away. So you can explore your design by playing with the different values of components, as well as all the Ctle values, right? In terms of the design exploration study that I have done, I was using this design. As you could see, it's very similar from the previous setting, but when I zoom into it, I can see I'm using the basically batch simulation, pointing to the CSV file, as I mentioned in my presentation. I'm not going to run, but it takes probably around half an hour to go through all the 96 different simulation cases, which is not too bad. At least I can save time not doing every single simulation one by one. So let me open up the results again, and when I switch it to the batch simulation, then you can see kind of plots that I have been using in my presentation. This is all 96 cases. I can pick up this batch index number. When I use the arrow in the keyboard, I can scroll through all different 96 cases. Not only being able to see what is the UI opening value, but also it automatically updates the eye data and also giving all the summary data for eye height and eye width and so on and so on. All right, this is about my demo. Thank you. Let me go to summary section. By the way, if you choose the path of getting the project file through MIPI webpage, then you must be a member. Otherwise, please contact us so that we can share the project file directly with you. As for the summary, I'd like to point out 3 things. First, by using TX-EQ and Ctle for equalizations, we proved that there was enough solution space for various channel configurations. Second, it is now possible to evaluate C-PHY designs with millions of bits using the channel simulation technology. Third, Pathwave ADS is only and unique a design platform for C-PHY that offers dedicated transmitters, receivers, and iProbe along with a channel simulator for C-PHY designs. Okay, that's great. Now let's move to Q&A session.
Okay, HeeSoo, here's your question from Mandeep. He asks, are there any layout recommendations for C-PHY since you have 3-wire group signaling versus 2-wire, which can be laid out differentially 100 ohms?
Yeah, that's quite an interesting question, but keep that in mind. C-PHY, from the TX 3-wire standpoint, is basically single-ended, not differential. It's a single-ended signals. By making the special signaling rule, they can encode, very specialized C-PHY signal. So designing the layout of the channel itself is basically designing the channel as a single-ended transmission lines. Second of all, many of the C-PHY designs are sharing existing D-PHY, which is differential, having the 4 lanes, as we discussed at the beginning. So basically, you can pick up those layout and plug in C-PHY by using the 3 wires instead of 4 wires. You can actually do the C-PHY designs top of the D-PHY. That's my kind of answer to you.
Great, thanks. And thanks for the question, Mandeep. Here's a question from Harry. Can IBIS model C-PHY, TX, and RX?
Yeah, that's a very, very interesting question. Right now, the model, what you saw in the presentation and demo are a C-PHY, TX, and RX without having any of IBIS model. Well, one of the idea why you could try that out is basically putting the C-PHY TX right after the C-PHY TX. 3 wires, you put the more like an IBIS pass-through model. So basically, that means you're bringing the IBIS information to a single ended signal, and then putting basically putting the transmitter as more like a pass-through, but added the IBIS model, then you should be able to include basically IBIS information into any of those 3 wires or signals. But top of it, if you wanting to add any of package information or any other RLC circuit that represent a certain parasitics, then you can plug in any circuit to those 3 wires so that you can reshape the waveform coming from the generic transmitter of C-PHY, and then it can be worked out that way. Thank you.
Okay, great. Thanks. Here's a question from Vahid. In slide 13, when the mask is being hit on its right side, is that okay?
I looked at every single. I think it's more like a graphic resolution. It is not really hitting the mask. There is sufficient kind of spacing due to the resolution of the picture or slide, seems like it's touching, but it's non-touching.
Okay, there was another question about that too. So, okay, good clarification. Here's a question from Joe. PCB simulation for combined D-PHY and C-PHY output driver. Is it two simulations, D-PHY, C-PHY, with common PCB elements?
I think it's supposed to be two different simulations because, as we discussed during the presentation, C-PHY has the different signaling. Like a D-PHY is more like a differential, and C-PHY is single-ended, but with the special encoding. So if we are using the same APCB channel, which is coming from D-PHY for C-PHY, we need to plug in a C-PHY transceiver and run the separate simulations. Same, if we are going back to D-PHY, then take out the C-PHY or disable the C-PHY transmitter and plug in D-PHY differential, a transmitter or receiver, and need to run the simulation again. So it's a separate simulation. Good question.
Okay, great. Here's a question from Kevin. I'm new to C-PHY and learned a lot from this presentation. Thank you. Would you please explain why C-PHY uses this complicated signaling instead simple NRZ or differential? What are the benefits?
Yeah, it's all about basically data transmission throughput. By using the spatial encoding for C-PHY, basically the bit rate is there are 2.28 bits in a symbol. So that means you can use the same channel to drive the same channel with higher data rate. Again, it is all about the throughput. Similar to the PAM4. If you know about the PAM4, it's a 2x. Basically using the same channel, but you can push out the 2x of more data. Same idea for the C-PHY at the moment. Again, it has the 2.28 times higher the number of bits in case of C-PHY, right?
Okay, great. And we have a lot more questions coming in, but I think we have time for one more, HeeSoo, and this one comes from Martin. It is really helpful and useful to have dedicated TX and RX for C-PHY simulations, but any comment or guidance on good channel modeling practices?
Yeah, that's a very, very important question. From the channel perspective, it is all passive network where all the signals will go through. But from my previous experience, how do we model the channel properly and definitely accurate? Since all the channel consists of various different elements, such as transmission lines, you may have the cable, you may have the PCB vias, and you may have the connectors, and so on and so on. Based on my knowledge and experience, again, most of the problems are coming from the transitions, not just straight transmission lines. Although we put the kind of bends to the transmission line, as long as we maintain the good ground return, then there won't be much of the problems coming into the quality of the signal. But again, more problems are coming from a transition, such as a via to transmission line to via, or putting the connector where a lot of signal distortions might be happening. So if you are really concerned about the channel modeling, then I really recommend to look into the special transition areas where you put a lot more efforts, including the more accurate modeling and simulations, and less focused on those transmission lines itself. So if you combine this kind of approach, then you're going to get the really good accurate models in a reasonable modeling time. Another kind of case is putting everything into more of the 3D, but it takes quite long. And I tell you, you don't have to do that. It's because you will be getting pretty much a similar level of the accuracy by putting the more focus on the transition area instead of a transmission line. That is kind of my experience, and one thing I like to share my experience and giving you my recommendation.
So this concludes today's webinar. Thank you for attending today's webinar brought to you by Keysight Technologies. Join us next month for the continuation of our Engineering Education webinar series, and enjoy your day.